Welcome back, everyone. Today, we're unpacking a really fascinating explainer on the fundamental duality that, well, literally powers our modern world. We're talking about the intricate dance between chemical and electrical energies. Because whether it's the battery keeping your smartphone alive right now, the rusting of an old iron gate, or the massive industrial extraction of pure metals, it all boils down to one incredibly elegant subdiscipline of physical chemistry. So we are going to visualize exactly how invisible electrons bridge the gap between chemical reactions and the electricity we use every single day. Okay, let's just jump right in. Here's the agenda for today's explainer. 1. What is electrochemistry? 2. Galvanic cells, generating power. 3. Cell potentials and NERST. 4. Electrolysis and Faraday's laws. And 5. Conductivity in solutions. So at its absolute core, electrochemistry is all about a two-way energy exchange. Basically, it's the study of the relationship between electrical energy and chemical changes. You can kind of think of it as a translator between two totally different languages of power. On one side, you've got chemical bonds breaking and forming, and on the other side, you have the raw flow of electric current. Electrochemistry is the bridge that allows one to transform into the other, and the whole shebang happens through the transfer of electrons in redox reactions. And this setup brilliantly illustrates the core narrative tension of our whole explainer today. The electrochemical universe is basically split into two main types of cells. On one side, we have galvanic cells. These rely on spontaneous chemical reactions. Reactions that just want to happen on their own to produce electrical energy. It's a natural downhill flow. Then, on the flip side, we have electrolytic cells. These are non-spontaneous. We literally have to force them to happen by pumping electrical energy in to create a chemical change. It's a lot like trying to push a heavy boulder up a hill. Section 1. Galvanic cells, generating power. To really grasp how this works, we need to zoom all the way into the microscopic level of a classic example, which is the Daniell cell. Here's how the mechanism breaks down step by step. First, over at the anode, we get oxidation. The zinc metal spontaneously loses electrons, turning into zinc ions that dissolve right into the solution. Second, those newly liberated electrons can't just float around in the liquid, right? So they travel through an external wire, and that creates the electrical current we can actually use to power a device. Finally, those electrons arrive at the copper cathode where reduction occurs. Copper ions in the liquid grab onto those incoming electrons and plate out as solid copper metal. So zinc sacrifices itself, copper builds up, and we get a nice, steady stream of electricity in the process. But wait, there is a huge catch here. If electrons just kept moving from the zinc side over to the copper side, a massive charge imbalance would build up and instantly stop the battery dead in its tracks. Enter the salt bridge. This is absolutely the unsung hero of the galvanic cell. It's usually an inverted U-tube filled with an inert electrolyte gel, something like potassium nitrate. As those negative electrons leave the zinc half cell, negative ions from the salt bridge flow right in to replace them, which maintains perfect electrical neutrality. It completes the circuit and keeps the whole system humming along. Section 2. Cell potentials and NERST. So we know electrons flow, but how hard do they push? Well, that is where cell potentials come into play. To measure this push, we use what's called the standard electrode potential. This basically tells us the tendency of an electrode to lose or gain electrons. But here's the tricky part. You can't actually measure the potential of one single isolated electrode. You can only measure the difference between two of them. Because of this, chemists universally agreed on a baseline. The standard hydrogen electrode is assigned a potential of exactly 0 volts under standard conditions. And standard conditions just mean 1 molar concentration, 298 Kelvin, and 1 bar of pressure. Literally every other element is measured against this absolute 0 point. When we take different elements and measure them against that hydrogen baseline, a really fascinating pattern emerges. Look at potassium. It has a highly negative reduction potential of negative 2.93 volts. This means it desperately wants to lose electrons, not gain them, which gives it the highest reducing power. On the flip side of that, silver has a positive 0.80 volts. It loves gaining electrons, so it has a very low reducing power. Essentially, the lower the reduction potential, the stronger the element is at forcing its electrons onto something else. Now, all of these standard potentials, they're incredibly useful in a pristine, perfectly controlled laboratory environment. But out in the real world, as a battery actually discharges, the concentrations of the chemicals change. The zinc gets more concentrated, the copper gets less. So we really have to ask, what happens to our voltage when our solutions are no longer sitting perfectly at that standard 1 molar concentration? And that is exactly where the Nernst equation comes to the rescue. It elegantly solves that exact problem, allowing us to calculate the actual cell potential, E cell, at any given moment. You just take the standard potential we just talked about, E naught cell, and subtract a value that's based on the temperature, the number of electrons being transferred, that's the N in the formula, and the log of the reaction quotient Q, which represents the current concentrations. So this equation is literally the mathematical bridge between perfect theoretical standard conditions and the messy, ever-changing reality of a real working battery.
Moving on to Section 3, Electrolysis and Faraday's Laws.
All right, now that we've mastered how to get electricity out of a chemical reaction, let's explore the exact opposite. Electrolysis is basically how we play God with molecules. By passing a massively strong electric current through a substance, like molten sodium chloride, for instance, we can force a completely non-spontaneous reaction to occur. We are literally ripping the salt apart. The positively charged sodium cations are forced over to the negative cathode, where they gain electrons to become pure solid sodium metal. Meanwhile, the negative chloride anions are dragged to the positive anode, where they lose electrons and bubble right off as toxic chlorine gas. It requires a huge input of energy, sure, but it lets us isolate pure elements that just refuse to exist on their own in nature.
And that brings us to a spectacularly specific number, 96,487. This is Faraday's constant. It represents the exact electrical charge measured in coulombs of one single mole of electrons. Just let the weight of that sink in for a second. By measuring the current we apply over time, we can count exactly how many moles of electrons we are pumping into an electrolytic cell, using this constant as our ultimate foolproof conversion factor.
Which brings us beautifully to Faraday's first law. The mass of the substance you can deposit or liberate at an electrode, which is represented by W, is directly proportional to the total electric charge passed through the electrolyte. Since charge is simply current multiplied by time, we get this really clean equation. Mass equals Z, which is just a constant for the specific element, times current, I, times time, T. Bottom line, if you want more pure sodium metal, you either need to crank up the amps, or you just run the machine for a longer time. It is beautifully, perfectly predictable.
Section 4, Conductivity in Solutions. So we've talked a lot about the electrodes and the math, but we also need to examine the actual physical medium carrying the current. When you add water to an electrolyte solution, two completely different things happen depending on how you're measuring it. Regular conductivity actually decreases upon dilution. Why is that? Well, because you're spreading the current-carrying ions farther apart. There are just fewer of them in any given cubic centimeter. However, and here's the twist, molar conductivity, which tracks the conducting power of exactly 1 mole of the dissolved substance, actually increases upon dilution. Even though those ions are spread farther apart, the total volume containing that one specific mole has expanded so much that it more than compensates for the drop in standard conductivity. Plus, the ions interfere with each other way less, so they can move around much more freely.
Finally, Section 5, Real-World Applications.
Okay, so we have all these laws, all these constants, and these big equations. But why does any of this actually matter to you and me outside of a chemistry lab? Well, because these principles are literally running the world. When you start up a traditional car, you are relying on a lead storage battery. It uses a lead anode and a lead oxide cathode, all bathed in sulfuric acid. When your car's alternator kicks in, it acts as an electrolytic cell, reversing the reaction to recharge the battery. Then we have fuel cells, which continually generate power by consuming fuels like methane or methanol. But here's perhaps the most surprising application of all, rust. The incredibly frustrating process of iron corrosion is actually just an unharnessed galvanic cell. The iron object itself acts as the anode, releasing electrons, while moisture and atmospheric oxygen act as the cathode. Your rusting bike chain? Yes, scientifically speaking, it's just a short-circuiting battery.
Crazy, right? We've seen how chemical energy creates electricity, and we've seen how electricity can force a kind of chemical rebirth. We can recharge the lead in our cars, and we can split salts right back into raw metals. Which leaves us with this final, kind of profound thought. If we can effectively reverse chemical aging by supplying electricity, just like we see in rechargeable cells in electrolysis, what is really preventing us from engineering the eternal, perfect electrochemical cell? It's a massive question, and it's one that continues to drive the very bleeding edge of physical chemistry and renewable energy research today. Thanks so much for joining me on this explainer, and remember to keep questioning the science all around you.